As I mentioned last week, the only other section that we have in Chapter 4 after this one is 4.9. But I always include that with Chapter 5. It's a very nice lead-in to integrals. So this is the last section for this Chapter 4 unit. Test is Friday. Wednesday, Thursday review, Friday test. And 4.1 through 4.6. So for 4.6 optimization, I have one. This is just one more example, but it is a little different from the examples we went through on Thursday. And then we'll review the process you want to think through when you work through an optimization problem. All right, but I need your attention up here, please. Okay, for this example, it says find the area of the largest rectangle that can be inscribed in a semicircle of radius r. So, I said when you solve an optimization problem, the kind of first two things I go between, well, maybe I'll explain this. I don't know if I explained it this way on Thursday. Usually when I read through a problem like this, I think to myself, what am I trying to maximize or minimize? What am I trying to optimize? And then I'll draw a diagram if it fits the problem. So what is it that we're trying to maximize or minimize in this problem? Area of a rectangle. So, and the rectangle, maximize area. And the rectangle specifically is inscribed in a semicircle of radius r. So I'm going to set up a diagram so I know how to label my rectangle, so I know how to set up my area formula for my rectangle. So whenever they describe a shape being inscribed within something, and sometimes they specifically give you an equation. I included the example to go through with you. An example, they don't give you the equation. But I'm going to draw this on a coordinate plane. And how I can set this up, I can set up a semicircle of radius r. I'm going to set it up with a center at the origin. I know it doesn't say that, but wherever I set it up, I'm going to be coming up with the equation for this. So I'm going to set it up. The easiest center for a circle on a coordinate plane is when it's at the origin. So I'm going to draw the upper half of the semicircle, so I'm in the positive quadrants for the y values at least. So there's the semicircle, and then if I have a rectangle inscribed in the semicircle, and this is of radius r, so I know this x value here would be positive r, this x value here would be negative r. A rectangle inscribed would look something like that. We're not doing integrals yet. What? We will, but not yet. All right, so I need, in order to set up an area function or area formula for this rectangle, I need labels for my rectangle. So I am going to label, and I chose this example to go through with you on purpose, because the semicircle is centered at the origin, I then can say, for example, this right half of my rectangle is symmetric to the left half of my rectangle. So I'm going to call this length here from the origin to the rightmost boundary of my rectangle. That is a distance of x, so whatever x value that would reach. And that means this distance here is also a distance of x, just in the opposite direction. So altogether then, the length of my rectangle would be 2x. And then the width or the height of my rectangle would be y, because it's equal to whatever the y value of that point would be the height. Okay, so my area formula for this rectangle, the length is 2x, the height is y. So the area would be 2x times y, or just 2xy. Okay, so optimization, it's good to recognize what are you trying to maximize or minimize and write an equation for it. And if it helps, draw a diagram so you know how to put together your equation for the area in this case. Then I said in order to find the max or min, this equation needs to be in terms of one variable, not two. So I need to be able to replace x or y with a quantity, so I just have something in terms of x or in terms of y. And where that's going to come from, and like I said, some problems will give this to you. I specifically chose a problem that doesn't because it's more challenging. We can use the equation of this semicircle to then make a substitution. So I'll just ask this, see if anybody knows, not that on an AP test you would be expected to just know this, but anybody know what the equation of a circle with radius r centered at 0, 0 would be? Yes. So I know this is reviewed geometry and in Algebra 2 with conic sections. For a circle, it's always x minus h quantity squared plus y minus k quantity squared equals r squared, where r is your radius, h, k is your center. And since we're at 0, 0, this would be the equation of the full circle. So the upper semicircle, if I solve this for y, you wouldn't divide by 2, but if I solve this for y, so subtract x squared, so y squared equals r squared minus x squared, and then take the square root. When you take a square root, you have a positive and a negative square root, but if I just have the upper half of the semicircle, it's just the positive square root. So y would equal the positive square root of r squared minus x squared. And this then I could substitute in for the y in my area equation. So I am going to have an area equation in terms of x and r, but r is the radius. So x is your variable, r is just representing a constant, it's your radius. So I would have the area is equal to 2x times the square root of r squared minus x squared. And now I have my area in terms of x. Okay, so then if I'm trying to maximize area, I need to find the maximum of this equation. So what do I have to find? Not the limit. Critical values. How do you find critical values? Derivative. So I need a prime.
Oh, no.
And what do I need to use to find the derivative? Product rule. Okay, so I'm going to let 2x be the first, and then I'm going to write the square root as the quantity r squared minus x squared to the 1/2. No, because you're taking the derivative with respect to x. Yep. So then derivative of 2x is 2. What do I need to take the derivative here? Chain rule. So I have 1/2 times the quantity r squared minus x squared to the negative 1/2 times. Now here, be careful when you take the derivative of the inside. What's the derivative of r squared? It is not 2r. It is 0. Why is it 0? R is a constant. So r squared is just like, say the radius is 3. 3 squared is 9. Derivative of 9 is 0. So this is not 2r.
Minus 2x.
Your derivative is just negative 2x.
So that just be negative x times r squared.
Yep, so you could write this as, and I'm going to write this as a square root on the bottom. So the 2's would cancel, so negative x over the square root of r squared minus x squared. So these 2's canceled out. This is a square root in the denominator. So if I put this all together, first times second prime would be the 2x times the x on the top. So I would have negative 2x squared over the square root of r squared minus x squared. And then plus, and I'm going to write this back as a square root here. So that quantity times 2 would be just 2, and then the square root of r squared minus x squared. Okay, and again, I chose this example on purpose. This is more messy or more complicated to simplify. So from here, to find your critical values, you're looking for where the derivative is 0 or where the derivative doesn't exist. And it's easiest to do that, in my opinion, if you have one fraction, because then you can set the top to 0, the bottom to 0 to get where the derivative is 0 or doesn't exist. So if this fraction, or if this term right now is over 1, I can multiply by the square root of r squared minus x squared on the bottom and on the top. So a prime would equal, and I'm going to write it as one fraction right away. So I'm going to have the square root of r squared minus x squared on the bottom. I still have the negative 2x squared from the first fraction. And then I would have plus 2 times, and when I multiply the square root of r squared minus x squared by itself, the square roots cancel, so you just have the quantity r squared minus x squared. So you no longer have a square root on the top. So I'll simplify that in one more step, still have the square root of r squared minus x squared. And then on the top, we would have, let's see, if we distribute that 2, we would have a 2r squared. And then we have negative 2x squared minus another 2x squared, so minus 4x squared. All right, actually, one thing I forgot to do is back up where we had our actual function. We could list a domain for this one. And that'll just make it easiest when you find your critical values. You don't have to set up a sign chart. You can just plug in the endpoints in your critical values. So if x is our variable here, what are the possible range of values for x? It has to be less than r and greater than 0. So x has to be between 0 and r. So if you even look at your diagram, so first of all, x can't be negative. That wouldn't make sense. So it has to be greater than 0. And if it's inscribed in a semicircle of radius r, it can't be larger than the radius. Okay, so this is just going to help after we find the critical values, because we have endpoints then. So if I go back to here, find where the derivative is 0. So that would be where the top is 0. And then where it doesn't exist would be where the bottom is 0. So that would really be where r squared minus x squared is 0. All right, so we are going to be finding values of x that are in terms of r. So if I solve that first equation for x, let's see here. I'll subtract 2r squared, so negative 4x squared equals negative 2r squared. Divide by negative 4, so x squared equals, I'll write it as r squared over 2, or 1/2 r squared. And then take the square root. And x can't be negative, so we just have a positive square root, so x would be the square root of r squared over 2, or you could simplify that if you wanted to, you don't have to. But that would be a critical value. And then where the derivative wouldn't exist is if this would be if x squared was equal to r squared, which if you take the square root when x is equal to r. So even though r is an endpoint, it's not really going to exist if x equals r. It's still an endpoint we can use for that closed interval method though, because it is a boundary. Okay, so we have our two critical values. And then we have to determine, really, because this is an endpoint, you're just double checking to see does this critical value actually give you the maximum area. And the problem does ask for the largest, or the area of the largest rectangle, so the area is going to be your answer, whatever the largest area is. So by the closed interval method, we are going to then calculate what is the area of the endpoints, 0 and r, and the area when x is the square root of r squared over 2. So what is the area when x is 0? What is the area when x is square root of r squared over 2? And the area when x is equal to the radius r. For when x is 0, so you're going back to, maybe I should have written this up here. We're going back up here. If x is 0, the area is 0. And if x equals the radius, in here you have r squared minus r squared, so that's also 0. So we just need to find this area, because this area is going to be our answer, the maximum area. So I'm going to plug this in. I'm going to show this work up here. So you would have the area is going to be 2 times the square root of r squared over 2 times the square root of r squared minus the square root of r squared over 2 squared. So I'm plugging in the square root of r squared over 2 for x. Okay, and then you simplify it. So, and I wrote this messy here. When you have the square root of r squared over 2 squared, that square and square root cancel. So this, and here these 2's also cancel. Nope, they don't. Just kidding. Don't cancel those. That was a test. Okay, so this is r squared minus, this just becomes r squared over 2, or 1/2 r squared. So now in this square root, r squared minus 1/2 r squared is 1/2 r squared. R squared over 2 and 1/2 r squared are the same thing. So these square roots are the same thing. And if you multiply them together, it's just r squared over 2. They cancel each other out. So this is just 2 times r squared over 2. 2's now do cancel, and the area is just r squared. Okay, So then, again, always look back. This question actually wanted to know what is the area of the largest rectangle. So this is the x value that gives the largest rectangle, and then this is the area of the largest rectangle that's inscribed in a circle of radius r. It's equal to the radius squared. So you could say the largest area is r squared. Okay, now, are all problems like that? No, I picked that one, like I said, on purpose. It's messy because you have r, you don't have an actual value, so it's more difficult to work with.
I can't take this one because my mind is